Hello everyone, welcome to this lecture of two-phase flow. My name is Mingcang Li. I am currently a faculty at the Department of Power Mechanical Engineering in National Tsinghua University. Per the request from the university, I'm recording and sharing this lecture for the NTHU OpenCourseWare project. The topic of this lecture is heterogeneous nucleation. Please be noted that the main content of the lecture materials is based on the reference book written by Professor Van Carey. Previously, we have introduced the homogeneous nucleation of vapor bubble in superheated liquid and the liquid droplet in supersaturated vapor. In many industrial applications, the nucleation of bubble or droplet is initiated by transferring heat through solid and fluid interfaces. Like this figure shown here for the example of an embryo vapor bubble formation in liquid. A homogeneous nucleation process may occur most likely in the region very close to the heated solid surface if the superheated condition corresponding to the kinetic limit is sufficiently reached. Another possible process is that the vapor bubble embryo forms at the fluid and solid interface. This process is called heterogeneous nucleation. In fact, this is a process that we encountered more in industries and daily life. Note that here we firstly make the assumption that the solid surface in contact with the liquid and the vapor bubble is perfectly smooth. In this case, the analysis described previously for the homogeneous nucleation can be directly extended for the heterogeneous nucleation process. As shown in this figure, the pressure of the liquid is dropped below the saturation pressure corresponding to the liquid temperature TL, and a vapor bubble embryo is formed in contact with the solid and the liquid interfaces. If we assume the shape of the embryo is a portion of a sphere, from a simple analysis of the geometry, the volume of the embryo, the area of the liquid to vapor interface, and the area of the solid to vapor interface can be derived as shown by equations 6.1 to 6.3. Then, we follow a similar analysis on the change in free energy associated with the formation of the embryo as we conducted for the homogeneous nucleation. Initially, the total free energy of the system is composed of the free energy of the superheated liquid and the interfacial free energy on the solid surface. This is shown in equation 6.4. Reminded that Nt is the total number of fluid molecules in the system, and the Gl is the free energy of the superheated liquid at TL and PL. Sigma SL is the solid-liquid interfacial tension. After the formation of a vapor bubble embryo, the total free energy of the system is equal to the sum of GL, GV, and GI. GL is the free energy contributed by the liquid. GV is the portion of vapor, and the GI is the free energy of those three interfaces. Then, apply the Young's equation. The change in system free energy associated with the formation of the embryo can be obtained as shown by equation 6.11. Since at equilibrium, the chemical potentials for vapor and the liquid have to be equal. If we take the radius of the vapor bubble embryo to be the radius at equilibrium, equation 6.11 can be simplified to that as shown in equation 6.12. Note that the Young-Laplace equation was used. The next step is taking the Taylor series expansion for delta G about R equals RE. Equation 6.13 can be obtained. Please be reminded that the embryo with a radius of RE is at an unstable equilibrium. That means embryos having a radius less than RE will spontaneously collapse, and embryos with a radius greater than RE will spontaneously grow. This conclusion is the same as we previously discussed in the last lecture for homogeneous nucleation. Also, if we define J as the rate of embryo formation, by following the same discussion and the derivation shown previously, a relation for J with the system properties can be obtained as shown in equation 6.17 for heterogeneous nucleation. This figure shows the variation of the rate of embryo formation for water as predicted by equation 6.17. Theta is the contact angle. Note that for theta equals 0, the result is the same as the homogeneous nucleation. If an appropriate threshold value of J is specified, one can estimate the onset of nucleation and the corresponding superheated limit temperature. By looking at figure 6.3, with the same superheated limit threshold of J, the corresponding temperature for the case with a smaller contact angle increases. Small contact angle means the solid surface is more hydrophilic, for example, most metal surfaces. On the other hand, a larger contact angle corresponds to a surface that is more hydrophobic, for example, Teflon. From the results of the analysis we have discussed so far, for a flat liquid-solid interface, in the case for water, it is required that the solid surface and the adjacent liquid to be superheated to around 300 degrees C for initiating heterogeneous nucleation of vapor bubble at atmospheric pressure. However, such a high superheated temperature is usually not observed in experiments or in our daily life. For example, boiling water in a metal pot usually requires a superheat of the pot surface at the bottom no more than 15 degrees C. Initiating of the bubble nucleation at a much lower superheat level is attributed to the presence of entrapped gas or vapor in small cavities on the solid surface. Figure 6.4a illustrates the possible mechanisms for the entrapment of gas or vapor. If the advancing contact angle is larger than the angle of the cavity, gas molecules are likely to be entrapped in the cavity while the liquid is covering the surface. Note that the advancing contact angle could be significantly greater than the static contact angle. Similarly, as shown in figure 6.4b, if the receding contact angle of the liquid is sufficiently small, then some trace amount of liquid might be left behind in the groove during a drying process. Also note that the receding contact angle could be significantly smaller than the static contact angle. For the onset of boiling, those gas molecules entrapped in the cavities may serve to provide nuclei for the formation of vapor bubbles. This in turn drastically reduces the requirement on the degree of superheat. These nucleation sites that are initially activated due to the entrapment gases could be deactivated if the boiling process is kept for sufficiently long. This is because the gas molecules entrapped in the cavity will gradually be removed along with the vapor bubble departed from the nucleation sites. Please be noted that the deactivation of nucleation sites will drastically affect the performance of heat transfer devices that rely on the phase change processes. Reentrant cavity is a design in the geometry of the cavity that helps to reduce the possibility of this deactivation. In this case, A vapor bubble, instead of a non-condensable gas bubble, can be entrapped in the cavity even after the fluid cooled down. According to the Young-Laplace equation, the pressure of the vapor in region 1 is lower than that in the liquid at region 2. Therefore, to condense the vapor completely to liquid inside this cavity, a substantial subcooling would be required. This helps to keep the vapor bubble entrapped in the cavity to be remained in vapor phase even after cooling the solid to environment temperature. By combining the Clausius-Clapeyron and the Young-Laplace equations, we can derive the relation between the radius of the vapor bubble embryo versus the degree of superheat. The minimum radius of an embryo in a cavity for the growth to continue can then be stated as in equation 6.27. This is the condition for the cavity to be active, because the embryo is allowed to grow continuously with supplying heat, like this one in figure A. In other words, for a given condition of superheat, a cavity will be active if the minimum radius of the liquid-vapor interface is above a critical value predicted by using equation 6.31. For a cavity with a radius of the mouth as capital R, the minimum interfacial radius corresponds to the maximum value of the ratio of mouth radius versus interfacial radius. As shown in figure D, if both the contact angle and the radius of the embryo are large enough, the maximum possible value of this ratio is 1. In this case, equation 6.28 can be used directly to predict the requirement on the degree of superheat for the cavity to be considered as active. This condition corresponds to the cases in figure B and C. In these cases, the radius of the cavity mouth is always smaller than the minimum radius of the vapor bubble embryo corresponds to the superheat condition. So, if the superheat can overcome the requirement of the embryo radius corresponds to the size of the cavity mouth, it can likely sustain the embryo growth beyond the size of the cavity. However, as can be seen from figure D, if the contact angle is small and the mouth of the radius is large, the ratio of the mouth radius versus the radius of the embryo is initially greater than 1. In this case, another model is required to determine if the cavity is active before this ratio becomes unity. Equation 6.28 cannot be directly used in this case, since it leads to underestimating the required superheat at the initial stage of the embryo growth. A model for this purpose is developed by Lawrence as discussed in the reference book. In this model, the size and the radius of the initial vapor embryo in the cavity is determined to be a function of the half angle of the cavity cone and the contact angle. Requirement for the cavity to be active is therefore determined by equation 6.29. Omega is defined as the ratio of the radius of the embryo versus the radius of the cavity mouth. Theta is the contact angle. Some results calculated from using equation 6.29 are shown in this figure on the right. Note that for omega greater than 1, the evaluation method shown in the previous slide and the equation 6.28 should be used. The Evulation cycle is the cyclic growth and the release of vapor bubbles at an active nucleation site. Considering the temperature of the liquid surrounding has a gradient along the direction of main heat transfer as shown in figure 6.11. A model for analyzing this process is proposed by Xu as discussed in the reference book. Basically, a transient one-dimensional conduction model is used to calculate the temperature distribution of the liquid surrounding near the nucleation site. Then, assume the embryo bubble would grow and the cavity would be an active site if the entire perimeter of the embryo bubble exceeds the requirement for superheat. This requires that the temperature at the top of the vapor bubble embryo, where Y equals B, to be no less than the equilibrium superheat temperature predicted from equation 6.40. Note that equation 6.40 is obtained by combining the Clausius-Clapeyron equation and Young-Laplace equation as previously did for deriving equation 6.27. This figure shows the results of equations 39 and 43. Equation 39 is the temperature distribution in the liquid resulted from the transient conduction due to the heated wall. Equation 43 is the equilibrium superheat temperature required at point B. Then, a cavity site is active if equation 44 is satisfied. So, it can be concluded that only those cavities within the range between those two intersections marked on this figure would be active. For values of Rc less than the minimum value, the required superheat cannot be supported by the surrounding liquid. For the values of Rc greater than the maximum value, the top portion of the embryo bubble experiences a temperature that is lower than the equilibrium superheat. Therefore, the bubble would start to shrink or collapse, and the growth cannot sustain. Following this discussion, a relation for estimating the minimum and the maximum cavity radius that will be active is derived as equation 47. Note that as the superheat decreases, the square root on the right-hand side of equation 47 goes to 0. So the maximum and the minimum radii for an active site becomes identical, which means only one size of cavity would be active. If the wall's temperature of the superheat keeps decreasing, the values of these two radii become imaginary. In this case, no cavity will be active. These results are better illustrated by figure 6.13. Three important features for heterogeneous nucleation of vapor bubbles on a heated wall can be concluded. First, a certain value of wall superheat is required before any cavity can become active nucleation sites. Second, above the superheat requirement to initiate nucleation, only a finite range of cavities can become active sites. Third, reducing the thickness of the thermal boundary layer, labeled as delta T here, will suppress nucleation. Let's consider the growth of a vapor bubble in a superheated liquid surroundings. From our discussion so far, it is clear that during the growth, the pressure and the temperature of the bubble have to be in certain ranges. PV is in between the pressure of the surrounding liquid and the saturation pressure corresponding to the temperature of the bulk liquid. TV is in between the saturation temperature corresponding to the pressure of the surrounding liquid and the real temperature of the bulk liquid. The rate of bubble growth is governed by the fluid momentum and the heat transfer across the interface. Therefore, there are two limiting cases of the bubble growth process. The first one is called the inertia-controlled growth. In this regime, PV is near its maximum value and the TV approximately equals T infinity. The growth of the bubble is not limited by the heat transfer across the interface, but is limited by how rapidly the vapor bubble can push back the surrounding liquid. The second regime is heat transfer controlled growth. In this case, TV is near its minimum value and the PV is close to P infinity since the radius of the bubble is large. Growth rate of the vapor bubble is limited by heat transfer across the interface. Here we show two models that had been derived for estimating the bubble growth rate for those two limiting cases. Figure 6.15 schematically illustrates the sequence of stages for a bubble growth process near a heated wall. After the departure of a bubble, it requires a period of time for the liquid at the bulk temperature T infinity be brought into contact with the hot surface and to rebuild the thermal boundary layer. In this period, no bubble growth takes place, so this time interval is termed as the waiting period TW. For a heat transfer controlled bubble growth process, analysis for the transient temperature distribution in the region near the bubble-liquid interface had been derived based on a model of one-dimensional transient conduction into a semi-infinite material. The results are shown in figure 6.16. The upper one is the temperature profile during the waiting period, and the lower one is after the waiting period where y equals 0 is at the vapor bubble surface. Equation 77 is the solution of the temperature profile. The rate of heat transfer and the resulting vaporization rate can then be determined with this equation. Based on it, a relation for the transient bubble radius variation can be derived as shown in equation 78. Also, by requiring that the temperature of the liquid at the top point of the bubble embryo with a radius equals the radius of the cavity to satisfy the equilibrium superheat condition, the time of waiting period can be determined. The departure of bubble is affected by several factors, such as buoyancy, surface tension, and viscosity. Therefore, it is reasonable to build correlations that relate the departure diameter versus these dimensionless parameters, such as Bond number, Jacob number, and Archimedes number. Table 6.1 provides a list of correlations in such kind for reference. The frequency of Evulation Cycle can then be estimated as shown in equation 96. Here is a summary of this lecture. We introduced the concept and the requirement for heterogeneous nucleation to take place. Then, we discussed the impact of the entrapped gas or vapor on the surface to the nucleation process. Then, we showed how to estimate the activeness of a cavity for the onset of nucleation. And finally, a complete model for analyzing the Evulation cycle for heterogeneous nucleation is provided.